Now, so what makes rational functions more complicated to graph are these asymptotes. So let's go over what they are and how to find them, and then we'll end with how to graph rational functions. So when you have a rational function, the first thing you need to do is factor the numerator and the denominator. Then, if both the denominator and the numerator have a common factor that reduces, so for example, if you have that f of x equals x minus 1 times x plus 2, so after you factor it, you get it as x plus 1 times x minus 1. Notice that both the numerator and the denominator have this factor that I can reduce. Then what we say is that the rational function has a hole at that corresponding x. So f of x has a hole at x equals, what's the corresponding x? X equals 1. Okay? So a hole, the function is not going to be defined there. There's going to be no function value there. Also, where does a rational function have vertical asymptote? Well, it's going to happen where the denominator is 0, after you did the cancellation of the common factors. So my function now, f of x equals, it's x plus 2 over x plus 1. So after I did the cancellation, my function is this. It's still a rational function, and it's going to have a vertical asymptote where the denominator is 0. So where x plus 1 equals 0, that is going to give me that the vertical asymptote is x equals negative 1. So shortcut for vertical asymptote is going to be VA. So at x equals negative 1, we're going to have a vertical asymptote, and we're basically going to draw it like this. The function is still not defined at negative 1. So the function is either going to go up to infinity or down to negative infinity around the asymptote. But it's never going to cross because there's no y value for x equals negative 1. So a graph never crosses a vertical asymptote because that value is not included in the domain. Now, horizontal asymptotes. Horizontal asymptotes have 3 cases. So if the degree of the numerator is less than the degree of the denominator, so let's see, if I have a function like this, let's say that the degree of the numerator is 2, so it will be x squared plus 3, for example, and then the degree of the denominator is 4, x to the 4th plus 3x plus 1. So if the degree of the top is less than the degree of the bottom, then the horizontal asymptote, HA, is the x-axis, which is y equals 0. So it will be y equals 0 is the horizontal line going through the origin. So this is y equals 0. So what happens here is this is the end behavior of the function. As x goes to negative infinity, the graph is going to approach this horizontal asymptote. And as x goes to infinity, the graph, in the end, is going to approach this horizontal asymptote value. Now, if the degree of the numerator equals the degree of the denominator, then the horizontal asymptote, the equation of the horizontal asymptote, is the ratio of the leading coefficient. So if I have that my rational function is 2x squared plus 3 over 3x squared plus x plus 1, the degree of the top is 2 and the degree of the bottom is 2, then the horizontal asymptote is going to be the ratio of the leading coefficients. So the horizontal asymptote is y equals 2/3. So it will be, let's say 2/3 is here. So the graph is going to approach 2/3 when it goes to negative infinity and when it goes to positive infinity. Okay, the graph can cross a horizontal asymptote. I can have the graph being like this. So see, as x goes to infinity, the graph approaches this value of 2/3 and it crossed the horizontal asymptotes. So a graph can cross a horizontal asymptote, but it cannot cross a vertical asymptote. If I plug in, it's fine. Now, the last case that we have is when the degree of the top is greater than the degree of the bottom. So if I have x to the 4th plus 5 over x squared plus 3, if the degree of the top is more than the degree of the bottom, then there are no horizontal asymptote. All right, so let's find the holes in horizontal asymptote of these of this function. So the first step is to factor the numerator and the denominator. It's almost factor, but I can also factor the x squared minus 1. And x squared minus 1 is x minus 1 times x plus 1. And then I have the 2x plus 3. And then the bottom, I can also factor x squared plus 5x plus 6. That's what two numbers multiplied together give me 6 and added together give me 5. Well, it's 2 and 3. So now that I have it factored, I can notice that x plus 1 is the common factor, so we're going to have a hole. So the hole is going to happen at x equals negative 1 because the factor is x plus 1. So at x equals negative 1. So the hole is actually a point, so I have an x value and a y value. So how do I get the y value? Well, I plug in x equals 1 into the function. So my function after the cancellation, you have it's x minus 1 times 2x plus 3 over x plus 2 times x plus 3. So then to find the second coordinate, so the x coordinate of the hole is negative 1. To find the y coordinate, I plug in negative 1 into the function. So let's see what is the function evaluated negative 1. It's going to be negative 1 minus 1, which is negative 2. Negative 1 times 2 plus 3, that's positive 1. Negative 1 plus 2 is 1. Negative 1 plus 3 is 2. So this is negative 1. So it so happens that the y coordinate is also negative 1, 1. Negative 1, negative 1. So when I'm going to draw this rational function at negative 1, 1, negative 1, negative 1, I'm actually going to have a hole. So it's not a vertical asymptote. It's a hole. Now let's find the vertical asymptotes. So now to get the vertical asymptotes, I'm going to look at the reduced function, and whatever makes the denominator 0, that's going to be my vertical asymptote. So x plus 2 equals 0 is going to give me the vertical asymptote x equals negative 2. And then x plus 3 equals 0 is going to give me the vertical asymptote x equals negative 3. So when I'm going to draw this rational function, I'm going to have a vertical asymptote at negative 2 and another vertical asymptote at x equals negative 3. And finally, horizontal asymptote. Well, what's the degree of the top? The degree of the top is going to be 2 because I'm going to have an x times a 2x. So that's going to give me 2x squared. And the degree of the bottom is also 2 because I'm going to have an x times an x. So what is the ratio of the leading coefficients? Well, the leading coefficient is going to come from multiplying this 2x with this x. So the leading coefficient at the top is 2. And then at the bottom, the leading coefficient is going to be 1. So the horizontal asymptote is y equals 2. 2 over 1. So the horizontal asymptote is going to happen right here. All right, so this is how we find this information when we're given the equation. If we are given the graph, we can just look at the graph and decide what are the vertical asymptotes, if there are any holes and stuff like that. So for example, for this one, where this is a rational function, are there any holes? We don't have any holes. I don't see any holes in the graph, so no holes. What are the vertical asymptotes? Well, these vertical lines, the first one is x equals negative 2. And then there's another one, x equals 2. So we have two vertical asymptotes. What about a horizontal asymptote? Oh, I see one right here, which is, this should be 1. So it's y equals 1. And what other pieces of information I can get from here? What are the x-intercepts? Well, I see that it crosses the x-axis here and here. This is -1 and this is 1. So x equals -1 and x equals 1. And then the y-intercept happens at 0.5. So we can get all this information from the graph. We don't have to do any algebra to get it. But if you have the function, you do all the algebra to get this information. Also, let's see, what is limit as x goes to infinity of this function f of x? Well, I know that as x goes to infinity, or as x goes to -infinity, the function is going to approach the value of the horizontal asymptote. So it's going to be the value of the horizontal asymptote, because as x goes large, I see that the graph gets closer and closer to the horizontal asymptote. And what is the value of the horizontal asymptote? Y equals 1. And similarly, limit as x goes to -infinity of the function is going to be, it's still this value of the horizontal asymptote y equals 1. So the end behavior now can be restated into this limit form that you're going to use in calculus. What about limit as x goes to -2? So as x approaches this vertical asymptote, let's say from the left, so I'm going to put a negative. Well, if I approach -2 from the left, where is the graph going? It's going up to +infinity. So we say that the limit is +infinity. What if I want limit as x goes to -2 from the right? Well, if I approach -2 from the right, where is the graph going? It goes down to -infinity. So -infinity. Similarly, if you look at limit as x goes to 2 from the left, you see that it's -infinity, and as x goes to 2 from the right, it goes up to +infinity.